So a few things here about phase diagrams. So it will be just conceptual. It's just an introduction to thermodynamics. So you see here those diagrams, they're gonna describe for a given substance the relationship between pressure, temperature, and phases. And they will all all the diagrams will look like that, except for water, which is really a special case. But you see here a phase, these lines here are called phase boundaries. So it means that, for example, at that point here, you have solid and liquid that will coexist together. So, for example, here you can start from C, and in that case, you are at a given pressure and you're going to increase the temperature. Okay. By increasing the temperature, you're going to bring thermal energy to the solid. So the molecules are going to start to move faster. Okay. So in that case, we're going to use this equation that will be how much heat is absorbed by the solid, and that will be translated by an increase in temperature. And of course, it depends on the material, so it depends on the specific heat capacity, which is how much energy is required to increase the temperature by 1 degree Celsius for 1 kilogram of substance, right? So heat is absorbed, temperature is going to increase. Okay, so it means that the kinetic energy per molecule is going to increase again. Okay, and here temperature will stay the same. So you have a coexistence between solid and liquid. Okay, the temperature will not change until all the solid has melted. Okay, so in that case, you use this equation here. So that will be the heat absorbed, that will be the latent heat or fusion, and that will be the mass of material. So the mass here is constant. Let's say the volume is constant here, and you go from here to there, and then you cross that boundary here where the two phases coexisted. Okay, and then you're going to go in the liquid phase, right? So then again, okay, the temperature is going to increase. So again, you can use this equation. Okay, so except now, it's still C for the liquid phase. Okay, so temperature will increase here until you reach that boundary here with the gaseous state. So for example, for water, you will be water here and steam there. And again, the temperature cannot change until all the liquid turns into gas. So for water, for example, that will happen at 100 degrees Celsius. So in that case, you will use that equation here with the latent heat of vaporization for a given mass. Okay, so here it will stay there at the same temperature until everything turns into gas, right? So we already discussed that, for example, for water, if you remember here, it's going to take a lot of energy here for a given mass of water, liquid state at 100 degrees Celsius to turn into steam. Okay? Now, so let's go back to the phase diagrams here, let's take another example here. If you go from A to B, okay, so it's at a lower pressure, for example, it depends on the substance, but let's say we are talking about CO2, so which is a dry ice. You see that at atmospheric pressure, so let's say this is atmospheric pressure, if the temperature is increased, then you go to the gaseous state. from solid to gas. Okay? So these are very important. So because it will be different for every substance. Here, if you go from G to H, so that will be a given temperature. Okay, so we keep the temperature constant. You see that here you have a liquid state, but then if you decrease the pressure, okay, you keep the temperature the same, but the pressure is decreased, you're going to go into a gaseous state. So if you have a container, for example, with liquid like water, if you have water inside the container and you start to pump the air out, so it means you're going to decrease the pressure. Okay, you're removing the air, pushing on the liquid, so the molecules can break free from the liquid state, and you're going to get a gas. So it will boil at a lower temperature, and then you have your gas. But you still have to cross that boundary here. So you decrease the pressure, and that at that point here, the liquid will start to evaporate. So interestingly, if you have a lower pressure for water, you cannot boil at 100 degrees Celsius. Okay, so on the mountain top, the pressure will be less, so the water will boil at a lower temperature. So you cannot have hard eggs, for example. Okay, so that's just an introduction. And then you have a critical point here, which is an interesting point. So if you go beyond that point here, you cannot distinguish, for example, between liquid and gas. It's something kind of sluggish. It's very hard. There is no sharp distinction here between the liquid phase and the gaseous phase, right? So we call that a supercritical fluid. So it's a very weird, dense gas. So we're not sure what phase it is in. And then you have another interesting point here, which is called the triple point. So in that case, the substance is in equilibrium in three phases, right? You have the solid state, liquid state, and gaseous state at the same time. So for water, it will happen at about 0 degrees Celsius, but at a pressure less than the atmospheric pressure. Okay, so water is very special. You see how all the substances, you have this line here between solid and liquid curved this way, but solid liquid for water will be curved in the other way. And that's because for water, you remember that solid has less density than liquid. So it means ice will float on liquid. Okay, so you have a lower density for the solid, and then the density will increase up to 4 degrees. So when you go to the liquid phase, the density will increase and then it will decrease again, right? So you have this very curious case here. So the density of ice is less than liquid. And then when it's going into the liquid state, the density is going to increase, okay, between 0 and 4 degrees Celsius. So we are in the liquid state and it's increasing, and then it's going to decrease again. And water has a density, the density of ice, so solid water is less than the density of liquid water, which is the only, it's a curious, I mean, it's necessary for life. So I guess Mother Nature knew what it was doing. Okay. So because of that, you have this curve here. Now, interestingly, water is the only substance. Okay. When you're let's say you are A Okay. So that will be at a given temperature. So here you have like a typo. You are at a given temperature, you're going to increase the pressure. Okay. You're going to go from solid to liquid. Okay. You can go from solid to liquid just by increasing the pressure, which is kind of counterintuitive, right? When you increase the pressure, it should be the opposite, right? You can go from liquid here to solid by squeezing, okay? But the opposite is weird, and that's what water is doing, okay? So you can go from solid to liquid by increasing the pressure. It's because of the structure of ice. Remember those hexagonal shapes, okay? So you can dig more into it, but it's interesting. You have the triple point here for water and the critical point here for water. Okay, so this is a summary that comes from the book from Wolfson, Fundamental of Physics. Okay, so usually when you increase a temperature, the temperature, and that will be my next video. I have one more video to do. So when you increase the temperature, a substance will expand, except for water that will contract when you increase the temperature between 0 and 4 degrees Celsius, right? So this is called thermal expansion, and we will talk about that next time. Now, you can have a phase change. Okay, during that phase change, the temperature has to stay constant, and you will use this equation. And then you have these diagrams with the relationships between pressure, temperature, and the phase, or the equilibrium between the phases. Okay? So that was very short.